All right, welcome to this video. Today I am going to be solving question 1 from quiz 2 of UBC Civil 311. It's a question on lateral earth pressures, and well, it seems pretty straightforward. There's a few tricks in there that really tripped a few people up, including myself. So I just thought it would be helpful for either if you're studying for this term's exam or if you're a future student just wanting to get an idea, just to show you guys how to solve this. So a retaining wall to provide lateral support to a stratified soil mass is presented in the figure below. I just had to redraw it myself since it was kind of mangled in the paper I have, but um, anyways, using the strength and density parameters given, estimate the crack depth in the clay zone and the lateral pressure distribution on the wall along line AC. Considering active backfill soil conditions, and then assume the following: a smooth wall and static groundwater conditions. Rankine theory is applicable, and there is no static pore water pressure arising from water filled in the tension crack zone. Okay, so the biggest thing here that we need to take note of is when we look at this soil strata, we notice that we have an SU value here. One thing to note is that when you see SU always means you're going to be using total stress analysis. So we need to keep that in mind when we do our calculations. So we'll look at our sand now. No SU value. What does that mean? We're going to be using effective stress analysis for this region. So now that we established that, let's start. So question 1, we need to get the crack length. So this one, really quick. Crack length is just equal to 2SU over gamma. And I don't think it's in the formula sheet, so it's just something you need to remember, but not too hard. So in this case, it's 2 times 12 over 16, which comes out to be 1.5 meters. And that's that. Now for part 2, we need to get the pressure distribution on that retaining wall. And to do that, especially since we're split between TSA and ESA, the best way is to make a table just to split everything up. So let's start by just saying, okay, what do we need? So we need where we are, our location. Next, let's figure out what is the pressure there. Is there any pore water pressure? What is the effective stress, if any? And then what is our total horizontal force or our effective horizontal force, depending on if it's ESA or TSA. So we have location A, we have B, and C. And you're thinking, okay, A, B, C. Wrong. We have that crack now. We have a 1.5 meter crack. So we got to make a new point, basically. Let's call it point CR for crack. And so now we know, okay, first location is location A. Next location is location CR. Next you'll say location B. Yes, but not exactly. B is where we kind of make that switch between TSA and ESA. So it's important that we consider the top portion of B and the bottom portion of B. So we'll say, okay, B top, and then B bottom. And then lastly, just point C. So now we can think. TSA from A to B top. So when there's TSA, that means that there's no effective stress. We're not doing effective stress. So that means we're not going to have any effective horizontal stress either. So we can automatically eliminate those. Now, same thing. For the effective stress, are we going to consider total horizontal stress? No, we're just going to consider the effective horizontal stress. So we're going to have no entries for the sigma XA. So let's start putting things in. Let's start at location A. Location A, we are at the surface. So what's our stress? 0. What's our pore water pressure? 0. Therefore, our horizontal force? 0. At the crack. At the crack, it's a 1.5 meter crack, and our gamma value is 16. So 1.5 times 16 is equal to 24 kPa. What's our pore water pressure in the crack? 0. Why is it 0? Statement C, right there. There's no static pore water pressure arising from water filled in the tension crack zone. That's one of the tricks there. So then, what is the horizontal total force? Well, I'll write the formula here. Sigma XA, and this should be given in the formula sheet, is sigma Z minus 2SU. So just like that. So what does that mean for us then? Well, okay, sigma Z is 24 minus 2 times our SU value, which is 12 kPa. What is that? Oh, well, it's 0. Just happens to be. Next, B top. So now we are right here. So we're 2 meters below. 2 meters times 16 is equal to 32 kPa. Now we're outside of the crack region though, right? We're past this point. We're now here. So that means that all the pore water pressure that's been gathered is valid now. So we're going to have 2 meters times 9.8 is 19.6 kPa. But the thing is, does it really matter? Not really, because we're not considering effective stress yet. So what does that mean? That means our sigma x is just 32 minus 2 times 12, which is 8 kPa. And then now we're done. We're done with TSA. Now to ESA. So exact same calculations so far for the bottom part. It's just 2 times 16. That's 32 kPa. And then 2 times 9.8 is 19.6 kPa. But now we have an effective stress value. So what do? We do total minus pore water pressure. So 32 minus 19.6 is 12.4 kPa. And so what does that make our horizontal effective stress value? Well, the formula for that, I'll do it in blue, is sigma x prime A is equal to Ka sigma prime Z. Now, what is Ka? Well, according to the formula sheet, Ka is 1 minus psi phi prime over 1 plus sine phi prime. What's our phi value? 30. So 1 minus sine 30 over 1 plus sine 30 comes out to be 0.33 repeating. We'll just say 0.33 for the calculations. So in this case, we're going to do 0.33 times 12.4, and then that gives you 4.1 kPa. And then lastly, at C, we're now 4 meters below, but we need to make note that our soil property changes. So we have 16 here and then 19.8. So it's going to be 32 times 16 plus 2 times 19.8. And that's going to be 32 plus 2 times 19.8 is 71.6 kPa. And then it's just 4 meters of water there, so 4 times 9.8 would be 39.2 kPa. So in our effective stress, we're just going to subtract the total from the pore water pressure. That gives 32.4 kPa. And then we're going to multiply it by 0.33. So 0.33 times 32.4, that will give us about 10.7 kPa. Okay, so now that we finished our table here, we can finish up actually, by just drawing what the distribution looks like on the wall. So I'll write our points A, B, C. They are 2 meters apart. 2 meters, 2 meters. And we also just have to make note that we have that 1.5 meter crack. And then it's just a matter of putting in our numbers. So we'll start with our TSA. So that's from A to the crack to the top of B. And we have values of 0, 0, and 8. So 0, 0 at the crack, and then a value of 8 kPa at B. And so then we just draw it like that. And that's it for TSA. Next we go to ESA, which is just B top and C. And those have values of 4.1 and 10.7. So probably around here is a safe guess, 4.1. And then 10.7 would probably be around here. So again, just connect it and draw the distribution. So now the last thing we need to consider is water. So I'm just going to plot kind of like a secondary axis. So it's just showing that this is acting on the wall, but just so it doesn't become a mess. So now we just consider the last column here. So A is 0, crack is 0, 19.6, 19.6 at B. So this is just one big B now with the same value. It's also a good way to check if you made a mistake. The B values for the pore water pressure should be the same. And then 39.2. So 0 at A, 0 at the crack, 19.6 at B, and then 39.2 at C. So 0 all along here. Then we're going from 19.6 to 39.2. And we can just draw our arrows now. Those are horrible, but they are horizontal. And so that's the final answer. Hope this video helped. Feel free to ask any questions if you have any. Thanks.